Welcome back to Curious Minds, a space where we explore mysteries, history, science, and the ideas that shape how we see the world. And every episode is a deep dive grounded in research, storytelling, and curiosity.
It's really great to be here to talk about this.
Somewhere in the Pacific Ocean, far from land and out of sight, there's a problem most of us never think about.
That is so true. And it's a problem that's, incredibly easy for us to ignore precisely because for almost all of us, it is completely out of sight. It's invisible.
It's not an island you can walk on. It's something more unsettling because it exists due to all of us. We are talking, of course, about the Great Pacific Garbage Patch.
Right.
And look, I think we have to tackle the elephant in the room right away. Or maybe the giant floating island in the room.
The trash island myth.
Exactly. The popular idea is still this, solid landmass of crushed bottles and old tires, something you could almost land a helicopter on.
Yes, that imagery have been so powerful for so long. And I think it comes from a need to make the problem feel tangible. If it's an island, we can put it on a map, we can sail to it, we can imagine shoveling it away.
You can give it a name.
You can give it a name.
Yeah.
But the reality is so much more complex. And frankly, from an engineering standpoint, it's a much harder problem to solve than a solid island would be.
So if you were in a plane flying from, say, Los Angeles to Tokyo, you wouldn't look down and see this giant, colorful continent of plastic.
Not at all. You would look down and see, well, the Pacific Ocean. It would look blue. You might not see anything out of the ordinary at all with the naked eye, certainly not from 30,000 feet.
So what is it then? If it's not an island, what are we actually talking about?
The sources, especially the really in-depth surveys from groups like the Ocean Cleanup and NOAA, they describe it very differently. The best analogies are a plastic smog or a cloudy soup.
A smog. That's a good one. It's more insidious, somehow. An island is contained, but a smog, it permeates everything.
It does. We're talking about a vast, dispersed region where debris accumulates. Now, don't get me wrong. There are big pieces out there. You'll find entire fishing nets, crates, buoys, things like that.
Right. Megaplastics.
Exactly. But the vast, vast majority of the count, the number of individual pieces, is microplastics. These are tiny fragments, technically anything smaller than 5 millimeters.
Smaller than a grain of rice.
Often much smaller, like dust. And they are suspended in the water column, mostly near the surface, but not just sitting on top of it. It's this suspension that creates the cloudy soup effect.
Okay, so what kind of density are we talking about? How cloudy is this soup?
Well, even in the center, the densest part of the patch, the density is estimated at about 4 particles per cubic meter.
4 particles per cubic meter? I mean, that doesn't sound like a lot. If you're imagining a landfill, that sounds like nothing.
It sounds low, but for the open ocean, which should be pristine, that is an astronomically high concentration. It's orders of magnitude higher than the surrounding ocean.
So if you were on a boat sailing through it, what would you see?
You might just think the water looks a bit murky, a little hazy. You'd see a piece of debris float by every now and then, maybe a bottle here, a piece of a crate there. You wouldn't necessarily grasp that you were in the heart of a global environmental catastrophe.
Not unless you were looking for it.
Not unless you dragged a specialized net, something called a manta trawl, through the water. Only then, when you pull it up and see the thousands of tiny plastic fragments you've collected in just a few minutes, only then would you understand the scale of it.
Wow. So our mission for this deep dive is to get past that trash island myth and really unpack the mechanics of this. We want to understand the physics that created it because it's not random.
No, it's pure physics.
We need to look at the bizarre new ecosystem that's evolving inside it, which honestly, that part of the research is one of the most surprising things I've read. And then finally, we have to talk about the massive, almost sci-fi level efforts to actually clean it up.
There is a lot of ground to cover, or I guess a lot of water to cover.
Let's start with the basic anatomy then. The map. We know it's in the Pacific, but that's, the biggest single feature on the planet. Where exactly is this thing?
It's located in what's known as the North Pacific Subtropical Gyre. The main accumulation zone, the densest part, is situated roughly halfway between Hawaii and California.
So it's not right off the coast. It's way out there in the high seas.
Way out there. In what is, for all intents and purposes, a biological desert in the open ocean. There's not a lot of life naturally in that specific region.
And when we talk about the size of the smog, the comparisons in the research are always just mind-bending. The sources cite an estimated surface area of 1.6 million square kilometers.
It's a number that's so big it's almost meaningless, right? So you have to use analogies.
Like Texas.
Exactly. It covers an area roughly twice the size of Texas.
Which is just immense. I mean, Texas is huge.
Or if you're in Europe, it's 3 times the size of France. It's about the
Yeah.
size of Alaska.
Mm.
You could fit 7 United Kingdoms inside of it. It is an enormous piece of our planet's surface.
I saw one calculation that said if you could somehow walk across it at a normal walking pace, it would take you 121 days.
4 months.
4 straight months of walking just to cross the trash field.
And that's assuming you could even find the edge. The boundary isn't a hard line on a map. It's not like crossing a border where you're suddenly in the patch. It's a gradient.
It gets denser as you go towards the middle.
Exactly. And the whole thing ebbs and flows. It shifts with the seasons. It's affected by weather patterns like El Nino and La Nina. But the core mass, that central zone, is incredibly stable. It's been there for decades.
So why is it stable? That's the big question. Why does all this trash gather there instead of just, I don't know, washing up on a beach in Oregon or Japan? This is where the gyre comes in.
This is the absolute key to understanding it. The North Pacific subtropical gyre, the physics here is just fascinating. A gyre is, in simple terms, a huge system of rotating ocean currents.
Like a giant, slow-moving whirlpool.
That's a great way to think about it. There are 5 major ocean gyres on Earth: the North and South Pacific, the North and South Atlantic, and the Indian Ocean. The North Pacific one is the biggest and most powerful.
So the whole ocean is spinning.
It is driven by 2 main forces: the prevailing winds and the rotation of the Earth itself.
The Coriolis effect.
The Coriolis effect. In the northern hemisphere, any moving object, whether it's air or water, gets deflected to the right. This sets up a massive clockwise rotation in the entire ocean basin.
And this rotation has boundaries, right? It's made of specific currents.
That's right. You can think of it like a giant roundabout. On one side, you have the California current flowing south along the U.S. coast. Then that feeds into the North Equatorial Current, which flows west towards Asia.
Okay.
Then it hits the powerful Kuroshio Current, which is like the Gulf Stream of the Pacific, shooting north past Japan. And finally, the North Pacific Current flows east, back across the ocean towards North America, completing the loop.
It's a carousel, a giant ocean carousel. But how does that trap things? Why don't they just keep spinning around the edge?
This is the really clever part of the physics. It's a phenomenon called Ekman transport.
Okay, let's break that down.
So the wind blows across the surface of the water, and you'd think it would drag the water in the same direction. But because of the Coriolis effect, the net movement of the surface water is actually at about a 90-degree angle to the right of the wind.
To the right, so the clockwise winds are actually pushing water inward.
Inward, towards the center of the gyre. All 4 of those currents on the edge are constantly gently pushing surface water toward the middle. This creates a very subtle hill of water in the center of the gyre. We're talking maybe a meter or 2 higher than the edges,
Wow.
but over thousands of kilometers.
So water is literally piling up in the middle.
A little bit, yes. And that creates a stable, calm, high-pressure zone. Sailors knew about these for centuries. They called them the doldrums or the horse latitudes because the winds there are so light, they'd get stuck for weeks.
And if the water is being pushed inward, anything floating on the water gets pushed inward too.
And that's the trap. Once a piece of plastic or a fish net or a log gets into that system, it gets pushed towards the calm center. And once it's there, there's no current, no force to push it back out. It's a convergence zone.
It's like the drain in a bathtub, but without the hole at the bottom.
That is the perfect analogy. The debris enters from the fast-moving currents on the rim. It spirals inward, and then it just stays. It accumulates year after year, decade after decade.
So physics built a natural garbage collector in the middle of our biggest ocean.
A very, very efficient one. And the problem is, in the past, if a tree or a massive seaweed floated in there, it would eventually biodegrade. It would rot and sink.
But plastic doesn't.
Plastic persists. It just breaks into smaller pieces, so the trap just keeps filling up.
Let's talk about how full it is. We've got the size, twice the size of Texas. What about the sheer quantity? The numbers in the research are, they're hard to even comprehend.
They really are. The most comprehensive study to date, which was a massive undertaking, combined old-school visual surveys from ships with high-tech aerial sweeps using C-130 Hercules aircraft with advanced sensors.
So they counted it from the sea and the sky.
Exactly.
Yeah.
And their mid-range estimate is that there were roughly 1.8 trillion pieces of plastic floating in the patch.
1.8 trillion. I feel like we get so numb to big numbers like trillion because we hear it in economics, but let's just pause on that for a second.
To try and give it some scale,
Hmm.
That is estimated to be 10 times more plastic pieces than there are stars in our entire Milky Way galaxy.
Wait, say that again?
10 times more pieces of plastic in that one patch than there are stars in the galaxy we live in.
That is an unbelievable statistic, floating between Hawaii and California right now.
It also works out to about 250 pieces of plastic debris for every single human being on Earth. Your 250 pieces, my 250 pieces. They're all out there.
And what about the weight, the total mass of all that?
The mass is estimated to be somewhere between 80,000 and 100,000 tons.
Which is, what's a good comparison for that?
It's equivalent to the weight of about 500 jumbo jets, or 3 Statues of Liberty. But this is where the distinction between the count and the mass becomes really, really important. It gets to the heart of the smog analogy.
Right, because if I hear 1.8 trillion pieces, I'm thinking it's all tiny dust. But if I hear 500 jumbo jets, I'm thinking it's all heavy, big stuff.
And the paradox is that it's both. This is what the data shows. By count, 94% of the objects are microplastics, the tiny fragments, the confetti, the smog.
94%, okay.
But by mass, 92% of the weight comes from the bigger stuff objects larger than 5 centimeters, macroplastics and megaplastics.
So the vast majority of the weight is in the big, visible objects, but the vast majority of the number of items is in the tiny, almost invisible stuff.
Precisely. And that's so critical for understanding the problem and for figuring out a cleanup strategy, which we'll get to later. The big stuff you see today, the ghost nets, the crates, the buoys, that is the source of tomorrow's microplastics.
It's future pollution waiting to happen.
Exactly. Plastic doesn't biodegrade. It doesn't rot. It photodegrades. The ultraviolet radiation from the sun makes it brittle. The constant motion of the waves breaks it apart. It doesn't turn back into organic material. It just cracks and shatters into smaller and smaller and smaller pieces.
So a single fishing crate that's floating out there today could become 1,000,000 or 1,000,000,000 microplastic particles over the next 10 or 20 years.
Correct. And that's why researchers get so excited in a grim sort of way when they find identifiable objects. They're like artifacts in an archaeological dig.
You're talking about that Game Boy cover.
The Game Boy cover from 1995. It's a perfect example. Right now, it's a recognizable object. You can hold it in your hand. But given another couple of decades of sun and salt, and it will be a cloud of gray plastic dust, impossible to ever clean up.
That Game Boy cover just really sticks with me. It's an artifact from my childhood. It's been floating in the middle of the ocean for my entire adult life, just bobbing there, slowly breaking apart.
And that's not even the oldest thing they found. They found a crate with a manufacturing date of 1977. That piece of plastic has been in the ocean longer than Star Wars has existed, and it's still there.
And we have to remember this is all just what's on or near the surface, right? We have to think vertically.
Oh, absolutely. This is maybe the most terrifying part.
Yeah.
The research suggests that what we see in the Great Pacific Garbage Patch, as horrifying as it is just the tip of the iceberg.
Because plastic sinks.
A lot of it does, yes. Estimates vary, but some suggest as much as 70% of all marine debris eventually sinks to the seafloor. Some plastics are naturally denser than seawater. Others start out buoyant, but then they get covered in algae and barnacles, a process called biofouling, which makes them heavy enough to sink.
So the seafloor beneath the gyre could be, what, a landfill?
It could be a new geological layer, a stratum of sunken trash, a hidden archive of our consumption habits that we can't even see or properly measure yet, is a haunting image.
It truly is. Okay, so I want to shift to what this stuff actually is. Because the public narrative, you know, the campaigns you see online, it's always about plastic straws, plastic bags, coffee cups. It's very focused on consumer waste.
That's the common story. And to be fair, globally, that's largely true. The general statistic is that about 80% of ocean plastic comes from land-based sources. It washes down rivers like the Yangtze, the Ganges, the Pasig, and out into the sea.
But the Great Pacific Garbage Patch is different.
It's very different. It acts as a kind of filter. The journey to the center of the gyre can take years. A lot of that flimsy consumer stuff, the thin plastic bags, the food wrappers, it often breaks down or sinks long before it can make that epic journey to the middle of the ocean.
So what's left? What's tough enough to survive the trip?
The hard, durable plastics.
Yeah.
And overwhelmingly, what the research found was fishing gear.
Ghost gear.
Coast gear. A major 2018 study published in Scientific Reports was a real game changer. It found that roughly 46% of the total mass in the GPGP is comprised of fishing nets alone.
Wait, almost half the weight is just fishing nets.
Just nets. And when you add in the other fishing-related debris, the ropes, the eel traps, the oyster spacers, the fish crates, the buoys, it accounts for the vast majority of the mass. This is primarily industrial waste, not post-consumer waste.
That just completely reframes the problem.
It has to. Because think about it. What is fishing gear designed for? It's engineered to be incredibly tough, durable, and weather-resistant. It's meant to survive for years in the harsh marine environment. So, of course, if it gets lost or abandoned, it's going to persist.
So while I'm feeling guilty about forgetting my reusable coffee cup, the much bigger problem, by weight at least, is industrial equipment being lost at sea.
It creates a real cognitive dissonance. Now, that's not to say we shouldn't reduce our single-use plastic consumption. We absolutely must. But if you want to solve the problem of the patch specifically, you have to look squarely at the global maritime and fishing industries.
And the research actually did that, right? They analyzed the debris to find out where it was coming from.
They did. It was like detective work. They collected and analyzed thousands of pieces of debris that still had legible writing, logos, or manufacturing marks on them.
And what did they find?
The most common languages identified were Chinese and Japanese. After that, Korean and English.
Which lines up perfectly with the major industrial fishing fleets that operate in the North Pacific.
Perfectly. The analysis points to 5 countries in particular: Japan, China, South Korea, the USA, and Taiwan. A follow-up study in 2022 was even more direct. It concluded that for the GPGP, it's likely that 75% to 86% of the floating plastic mass originates from offshore fishing and agricultural activities.
That statistic just completely flips the script. It's not just litter, it's a direct byproduct of a global industry.
It is. And that means the solution is much more complicated than a simple "don't litter" campaign. It involves things like international maritime law, regulations for fishing gear, and maybe even tracking systems for nets and traps.
So let's talk about the impact of all this stuff being out there. Because obviously, a giant floating net is a death sentence for pretty much anything that swims into it.
The ecological damage is profound, and it happens on several different levels. The most direct and visceral one is entanglement. This is what we call ghost fishing.
The nets keep on fishing even after the fishermen are long gone.
They never stop. They're designed to catch marine life, and they just keep doing it. A big tangled ball of nets, sometimes called a ghost net knot, can be the size of a car. It drifts silently through the ocean, snagging everything in its path.
Turtles, sharks.
Turtles, sharks, seals, dolphins, even small whales. The animals get tangled up. They can't surface for air. They can't hunt for food. They suffer horrific injuries, and they ultimately die. And the truly grim part is that as the animal decomposes and falls out of the net is just rebaited. It's ready to catch its next victim. It's a perpetual killing machine.
That is just a horrifying image. And then, of course, there's ingestion. We've all seen those pictures of the albatross.
The albatross chicks on Midway Atoll, it's absolutely heartbreaking. Midway is right on the edge of the patch. The parent birds fly hundreds of miles, skimming the surface of the ocean for food like squid and fish eggs.
But they find plastic instead.
They find plastic. To an albatross, a red bottle cap or a plastic lighter floating on the surface looks a lot like food. So they scoop it up, and they fly back to their nests and regurgitate this plastic into the mouths of their chicks.
And the chicks can't digest it, obviously.
Of course not. Their tiny stomachs fill up with indigestible plastic. They feel full, so they stop begging for food from their parents, but they're receiving no nutrition.
Yeah.
They are slowly and agonizingly starving to death. Or the sharp plastic edges puncture their internal organs. We are seeing entire generations of seabirds being wiped out by this.
And what about sea turtles? I know they're particularly vulnerable.
They are. Turtles are primarily visual hunters, and to a sea turtle, a floating plastic bag looks almost identical to a jellyfish, which is a primary food source for many species.
It's a case of mistaken identity.
A deadly one. A recent study found that for sea turtles that enter the GPGP area, a staggering 74% of their diet, by dry weight, is plastic.
3/4 of what they are eating is plastic. That's not a sustainable diet. That's an extinction-level event for those populations.
It is. But there's a third level of harm that's even more insidious because it's completely invisible, and that's bioaccumulation.
Okay, so this is the chemical side of the problem.
This is the chemical side. See, a piece of plastic in the ocean doesn't just stay inert. It acts like a little chemical sponge. It has a hydrophobic surface that attracts and absorbs other persistent organic pollutants, or POPs, that are floating in the water.
Things like pesticides and industrial chemicals.
Exactly. Nasty stuff like PCBs, DDT, flame retardants. These toxins cling to the surface of the plastic, reaching concentrations up to 1,000,000 times higher than in the surrounding seawater.
So every piece of microplastic becomes a tiny poison pill.
A tiny, toxic time bomb. A zooplankton eats that piece of plastic. A small fish eats thousands of zooplankton. A tuna eats hundreds of those small fish. The plastic itself might pass through, but the toxins don't. They get stored in the fatty tissues of the animal.
And they move up the food chain.
They biomagnify at every step. By the time you get to the top predators, the tuna, the sharks, the dolphins, the concentration of these toxins could be enormous.
And we are at the top of many of those food chains.
We're absolutely at the top. We eat the tuna that ate the fish, that ate the plankton, that ate the plastic. We are, in effect, poisoning our own food supply. We're now finding microplastics and their associated toxins in human blood, in lung tissue, even in placentas. We don't fully understand the long-term health consequences yet, but the connection is undeniable.
That really brings the problem from out there in the middle of the ocean to right here on our plates. It's terrifying.
Right.
And this is where this deep dive gets really strange. The research points to something completely unexpected. Amidst all this death and destruction, new life is adapting.
The plastosphere.
It sounds like a title from a bad 1950s sci-fi movie, but it's a real documented phenomenon. Tell me about these neopelagic communities.
This is a truly profound and unexpected discovery, and it's forcing marine biologists to rethink a lot of things. Historically, the open ocean surface, what's called a neustine layer, is a very barren place. There's no structure, there are no rocks, no reefs, no seabed to attach to. It's just water and sunlight.
So only very specialized creatures can live there.
Very specialized ones that evolved to float, things like the Portuguese man-o'-war or little floating snails. But now we have introduced millions of tons of permanent hard substrate into this environment. We've created trillions of floating plastic reefs.
And things are moving in.
Things are moving in. And what scientists are finding, to their astonishment, is that coastal species animals that are supposed to live in tide pools or on piers and buoys are rafting out into the middle of the ocean on this trash and establishing permanent reproducing colonies.
You're kidding? So you're finding, like, barnacles and crabs in the middle of the Pacific, thousands of miles from any coast.
Yes. Sea anemones, crabs, sponges, hydroids, coastal barnacles, they are thriving out there. They are living and reproducing for generations on this floating plastic. They have created an entirely new artificial ecosystem.
In a life finds a way kind of sense. That sounds almost cool, but I'm guessing there's a pretty big catch.
There's a massive catch. These coastal species are, by nature, aggressive competitors. They're used to fighting for every square inch of space on a rocky shore. Now they've been transported to the open ocean, where they are competing with and preying upon the native open ocean species who have never had to deal with this kind of competition before.
So it's a biological invasion.
It is a biological invasion on a planetary scale, facilitated by our trash. We are fundamentally altering the ecological balance of the open ocean. And there's another dangerous feedback loop. As these heavy coastal organisms grow on the plastic, they add weight.
And they eventually make the plastic sink.
Exactly. They may be acting as an elevator, accelerating the transport of plastic and all its attached toxins from the surface down to the deep sea, where it can impact entirely different ecosystems.
So this creates a bizarre ethical dilemma. If we go out there and clean up all the plastic, we're technically destroying this new, albeit unnatural, habitat.
It's a genuine paradox. By removing the pollution, we are killing the life that has come to depend on it. But the overwhelming scientific consensus is that the plastosphere is a pathological ecosystem, a dangerous one. It shouldn't be there.
It's like a tumor. It's living tissue, sure, but it's a cancerous growth on the ecosystem.
That's a very harsh but probably very accurate analogy.
Okay, so let's talk about surgery. How do we remove this tumor? For years, the common sense question was, why don't we just get a bunch of boats with big nets and scoop it all up?
It seems so simple, right? But the problem is the sheer scale. Again, 1.6 million square kilometers. NOAA actually did a calculation on this. They estimated it would take 67 ships working nonstop, 247, for a full year to clean up just 1% of the North Pacific.
1% in a year with 67 ships. And you'd be burning an incredible amount of diesel fuel the whole time.
A catastrophic amount of fuel.
Yeah.
The carbon footprint of the cleanup would be a disaster in itself. And, even more importantly, if you just use standard nets, you'd be scooping up everything.
Bycatch.
Massive, massive bycatch. You'd be killing the very turtles, fish, and plankton you were trying to save. You'd effectively be strip mining the surface of the ocean.
So we need a smarter, more delicate approach. And this is where the story of Boyan Slat and the ocean cleanup really begins.
It's an incredible story. He was just a teenager, 16 or 17, on a diving trip in Greece. And he realized he was seeing more plastic bags in the water than fish. And instead of just being depressed about it, he went home and started sketching ideas.
He gave a TEDx talk that went viral, and it just took off from there.
It did. He dropped out of his aerospace engineering degree and founded this nonprofit. But his first major design, it didn't really work, did it?
No, that was System 001, which they nicknamed Wilson. The idea was to anchor a huge, U-shaped floating barrier to the seabed and let the ocean currents passively push the plastic into it.
It's a brilliant idea in theory.
Mm-hmm.
But the forces out there in the open Pacific are just monumental. The system couldn't hold its shape, it moved unexpectedly, and eventually it just broke apart. The ocean was too powerful.
So they had to go back to the drawing board. They iterated. They came up with System 002, or Jenny.
Jenny was the big breakthrough. They realized they couldn't fight the ocean. They had to work with it. They abandoned the passive idea and moved to an active system.
So now they use ships to tow the barrier.
Yes, they have two large vessels, one at each end of the U-shaped barrier. They tow it through the water. Now, that does bring back the burning diesel concern, and that is a valid criticism they are constantly working on by trying to find more carbon-neutral fuels.
But the towing gives them control.
It gives them total control over the speed. And this is the absolute key to solving the bycatch problem. They tow the system at about 1.5 knots, which is slower than a normal walking pace.
So fish and turtles can just swim away.
They can easily swim away, they can go around it, they can dive under it. It's moving too slowly to pose a threat. But the plastic, which has no propulsion of its own, just gets gently collected by the barrier.
And now they're scaling this up massively with System 03, which they've nicknamed Josh.
Josh is a true monster of a system. The floating barrier is 2.2 kilometers long.
1.5 miles wide, just trying to picture that. A floating net system 1.5 miles across being towed through the ocean.
It's a massive feat of engineering, and they're not just dragging it around blindly. This is where the high-tech element comes in. They use artificial intelligence and sophisticated computational models of ocean currents
To find the plastic.
to find the plastic hotspots. The garbage patch isn't a uniform smog. It has dense patches and thinner patches, like clouds in the sky. Their models predict where the densest clouds of plastic will be, and they steer the system directly towards them.
That makes it much more efficient.
Dramatically more efficient. The plastic is then funneled down the U-shape into what they call the retention zone at the back. It's basically a giant, incredibly strong garbage bag.
And once that's full, they just haul it aboard.
They close it off, detach it, haul the massive bag onto the deck of one of the ships, and empty it out.
I've seen videos of that moment. It is a truly visceral sight. It's not clean, separated recyclables. It's this gray, slimy, tangled, stinking mess of nets and broken plastic.
It's a hall of misery. It's covered in that plastisphere life we were talking about. And the crew has to get in there and sort through it all by hand, separating the different types of plastic.
Let's talk about that human element. We talk about the AI and the systems, but there are people, men and women, living out there for weeks and months at a time on these ships.
It's incredibly grueling work. They're offshore for extended rotations, dealing with the famous North Pacific storms, the isolation, the sheer monotony, and the psychological weight of confronting that much waste every single day.
But they must feel a sense of purpose.
Immensely. In the interviews with the crew, they all talk about that moment. The moment the hull comes on deck. They know that every ton of ghost gear they pull out of the water is a ton that will not be entangling whales and turtles for the next 100 years.
Do we know how much they've removed so far?
The number is constantly climbing, but they've removed several hundreds of thousands of kilograms. And their stated goal is just breathtakingly ambitious. They aim to clean up 90% of all floating ocean plastic by the year 2040.
90% by 2040. I mean, is that even possible?
It's an astronomical goal.
Yeah.
It would require a whole fleet of these System 03-sized platforms working constantly.
Yeah.
But this is the critical point they always make. Cleanup is only half of the solution.
Right. If the tap is still running full blast, mopping the floor is a fool's errand.
Exactly. You can have the best mop in the world, but it's not going to solve the problem. You have to turn off the tap. This is the difference between cleaning up the legacy plastic, the stuff that's already out there, and stopping the new emissions.
So how are they trying to turn off the tap?
This is the other side of their operation. They're deploying what they call interceptors in some of the world's most polluting rivers.
Acting as a goalie for the ocean.
A perfect description. It's a solar-powered automated barge that they anchor in the mouth of a river. It has a barrier that funnels the floating river plastic towards it. A conveyor belt lifts the trash out of the water and drops it into dumpsters on the barge.
And it's all automated.
Fully automated. When the dumpsters are full, it sends a text message to a local operator who comes and empties them. They have them running in places like Indonesia, Malaysia, and the Dominican Republic.
That seems so much more efficient. Catching the trash in a narrow river instead of chasing it across the vast ocean.
It is infinitely more efficient. But you need to do both. You need the interceptors to stop the flow of new plastic, and you need the ocean systems to clean up the tens of thousands of tons that have already accumulated for decades.
But even that feels like it's downstream. The ultimate upstream solution has to be just making less plastic to begin with.
And that takes us from technology and engineering to global politics. It brings us to the negotiations for the UN Global Plastics Treaty.
This has been called the Paris Agreement for Plastic.
It has that potential. In 2022, 175 nations agreed to develop a legally binding international treaty to end plastic pollution. The negotiations since then have been incredibly intense.
What's the main point of conflict?
It really comes down to this. Do you focus on cleaning up the mess, or do you focus on preventing it? The powerful petrochemical lobby, the oil and gas industry, is pushing very hard for the treaty to focus on waste management and recycling.
Because 99% of plastic is made from fossil fuels.
It is their backup plan. As the world moves away from burning fossil fuels for energy and transport, the industry is banking on a massive expansion of plastic production to secure their future profits. So they want the responsibility to be on cities and consumers to recycle better.
But environmental groups in many nations are pushing for something much more radical.
They are pushing for a cap on virgin plastic production, to actually mandate making less of this stuff in the first place, to force manufacturers to redesign products to be reusable or truly biodegradable, not just single-use.
Because the reality is that plastic recycling has been, well, a colossal failure.
It largely has.
Yeah.
The statistic is that only about 9% of all plastic ever produced has been successfully recycled. The economics just don't work. It's almost always cheaper to make new virgin plastic from oil and gas than it is to collect, sort, clean, and reprocess old plastic.
So the treaty needs to fundamentally change those economics.
It has to. It needs to force the true cost of plastic to be included in its price. Right now, a plastic bottle is cheap for the consumer because neither the consumer nor the company pays for the environmental damage it will cause for the next 400 years.
It's the classic tragedy of the commons.
The ultimate tragedy of the commons. We privatize the profits from making the plastic, and we socialize the cost of the pollution. And the ocean, which belongs to no single country, becomes the world's dumping ground.
It makes you think about our legacy. We define past eras of humanity by their materials. The Stone Age, the Bronze Age, the Iron Age. Are we living in the plastic age?
Many scientists believe we are. They call this new geological epoch the Anthropocene, the age of humans. And geologists are finding that when they look at sediment layers being laid down right now in lakes and on the seafloor, there will be a clear, distinct layer defined by our synthetic waste.
So in a million years, future archaeologists or whatever aliens come after us will dig down and find this thin stratum of compressed bottle caps and polyester fibers.
Technofossils. That will be the marker of our time on this planet, a layer of our durable, non-degradable garbage.
That is an incredibly sobering thought. We are literally creating a new layer of the earth out of trash.
It is, but I also think there's a flip side to that. We are the species that created this problem. We invented this material. We engineered it. And that means we also have the capacity to engineer our way out of this crisis. We have the science, we have the technology, and we are finally starting to build the political will.
It does feel like we're at a turning point. The old trash island myth allowed us to dismiss it because it sounded too cartoonish to be real. But this new understanding of a plastic smog is so much more scientifically grounded and so much more terrifying.
It is. But seeing the problem clearly for what it really is the first and most important step to actually solving it. We know the physics, we know the sources, we have the tools. The question is no longer can we fix this, but will we?
The garbage patch isn't proof that the ocean is dying.
It's proof that our habits travel farther than we think, and that we still have time to change them.
So that's a wrap on today's episode. Thank you so much for spending your time with Curious Minds. If you found this discussion interesting, feel free to like, comment, and share your thoughts. And as always, stay curious, stay grounded, and hope to have you join us for the next one.